Hocam derse başlamadan bir şey sorabilir miyim? Hocam derse başlamadan bir şey sorabilir miyim?
Evet.
Bizim vize durumumuz belli mi? Vize olacak mıyız veya quizler mi vize yerine geçecek?
Dur yapacağız o konuda. Okay, everybody. Today we are starting today at 9 o'clock we have our quiz number 2. It will be through Teams again. During the quiz, you are going to use your cameras, turn on your cameras, and we are recording your videos. It will be just 20 minutes, two questions and 20 minutes. Okay, today we will start our new topic, memory management, chapter number 3. Which is about memory management. We say that, come on, this one doesn't go away. Let me try to fix it. No, yeah, okay. Go away and this. Okay, so we say that, okay, however, how much memory you have doesn't matter. You will have programs to fill the available memory, okay? So there is no too much memory. It is always memory is not enough. Okay, you have to be very careful about your primary memory, also your secondary storage too. You will run out of them no matter what. Even though we have millions or billions of times more storage in our ordinary computers nowadays compared to 1960s, memory is still not enough. This computer in 1960s, it is $20 million in today's money. Okay, IBM 7090, $20 million, and it had just 32 kilobytes or kilowords. Okay, so $20 million, 32 kilowords. And you see, it is not that much. And people used to live with that kind of memory, and they complained about memory is not enough. Nowadays we have on our ordinary computers, desktop computers, portables, we have 8 gigabytes, 16, 32 gigabytes of memory, and we say that memory is not enough. So we have to manage the memory. It's a resource. Okay, memory is a resource. It has to be managed, and we have operating system to manage it, luckily. Okay, so what do we mean by this? Why do we need to manage the memory? Let's look at a few cases. I mean, if like the CPU abstraction, remember for the CPU abstraction we had the processes. Okay, like the CPU abstraction, um, uh, uh, if you have a single process running on a computer without any operating system, or a single process, single operating system, that's it. You don't need the idea of processes, okay? You don't need maybe protection. You don't need more than one program. The life would have been simple, but our computers doesn't work that way. We run many processes at the same time. And for the memory, it's the same thing. In the early days of computers, okay, it used to be like this, okay? There was one user program at the higher part of the memory. At the lower part of the memory, we have our operating system. Okay. And whenever I needed something from the operating system, I make a function call, not even a system call, just a function call. Okay. And if we are sure about our operating system, if we are not upgrading it, then we may prefer such an architecture. We may say that, okay, user program is in the RAM, but operating system is in the read-only memory, right? So that would be the second thing. So some embedded systems work that way, okay? Or in C, we have some fixed part of the memory at the upper part of the memory. Then we have our user programs, okay, user program, just a single program, and we have our operating system in the RAM in the lower part of the memory. And there was no protection. There was no second program. Okay, there is no scheduling and etc. This was the case for those computers. Old mainframes where the memory is very limited. Embedded systems, well, for the embedded systems, memory and CPU is already limited. And early MS-DOS systems are really, they were CPU and memory limited. They are very, very weak systems. Okay. But this is not the case. We have to put many programs. We have to manage many programs at the same time in our memory. So we need to manage the memory too. Remember the operating systems? What did we say about the operating systems? We said that operating systems are a piece of software that is used for managing the resources, right? Managing the resources and abstracting away the details of the hardware. You may say that I understand the I understand the management of the memory because many programs need to use the same memory. That's the management. How about the details of the memory? What is so complicated of the memory? Well, for this kind of memory, maybe everything is clear. There is no complication, okay, for this kind of system. But as you are going to see, memory is not simple as this anymore. It has more components such as a memory management unit. Somebody has to take care of memory management unit, and that's going to be the operating system. Okay, let's look at this example. Let's say I have a very simple computer and I have 16 kilobytes of RAM, almost 16 kilobytes. Okay, I loaded the program to this computer and going from, okay, address number 0 to some large number, we are loading this program and we are going to run it. As soon as I load the program, my CPU starts executing this instruction, jump 24. I jump to 24. I move some data, some edit some data, whatever it is. So this is program A. This is our program A. This is our program A. Program B is similar. It is doing I loaded the program. The first instruction is jump 28. I jump to 28 and so it's another program. Let's say I have large enough memory now. I like to do multi-programming. Okay, I like to do multi-programming. And I like to, okay, load two programs at the same time because I have large enough memory now. A program A and program B will be loaded at the same time. So I loaded the program A in the first 16 kilobyte of the memory, and I loaded program B at the upper part of the memory. And now I am doing this scheduling. Sometimes program A runs, sometimes program B runs. When program A runs, it's going to do the same thing. Jump 24. 24 is here, and I continue. But when program B starts running, it says jump 28. Remember, it was like that. It was like that. 28. Okay. So it used to jump to this location. But 28 is in the address space of the program A. Okay. Well, that's a problem. That's obvious. That's a problem. That's obvious. Why are we having this problem? Because operating system or the hardware is not helping at all. Okay. There is no protection between A and B. A can read B's data, B can read A's data. Also, there is this relocation problem. Relocation problem. Okay. If I relocate program A or program B, other than some other part of the memory, other than 0, some other part of the memory, they will not run. Okay. They will produce nonsense results. They will crash most probably. Okay. So we have to solve this problem. We have to address this relocation problem. Even with the relocation problem, I have to address this protection. Okay. A should not be reading B's data, vice versa. Okay. So these are the stuff that we need to address in order to have more than one program running in my memory. Okay. So let's look at this idea of static relocation. Idea is this. Okay. At program load time, when I load this program B here, okay, I will find all the instructions that refer to memory. For example, this 28, right? I will add this 28 with this 16,384 number, these two. I will add them, okay? I will add them, these two, I will add them. And this is going to give me a new address, which is going to be this one, right? If I add them, it will be 16412. Okay? So that means what? I am adding the actual offset to the presumed location specified by the compiler and linker. Okay. So that in a way that I am modifying my program in a way that all of these memory references for B is going to be different now. Okay. I did the same thing for A2, but since my relocation will be at 0, nothing changes for A. So the idea is modify all these memory references when you load the program. But how do I know that which instructions are memory references? My compiler is going to tell me those, compiler and the linker. Compiler and the linker has to be specialized, okay? And they are going to tell me that I should change this and this and this. Okay? So that's the thing. So it is kind of expensive. Why? Because every time I load a program, I need to make this modification. But that's okay. I'm going to do this only once when I load the program. Okay, it kind of does that, but there is no protection again between these two programs. There is no protection, right? A, knowingly or unknowingly, can read and write to B's address space. Okay, there is no protection. And the second thing is, if I try to load everything to my memory, okay, I will run out of my memory. Remember, on this computer, I am running more than 100 processes. Okay, I'm running more than 100 processes, and each one needs gigabytes of memory. I don't have that kind of memory. Okay, I don't have that kind of memory. So what am I gonna do? What am I gonna do? I need to find some other solution. So this um, solution static relocation. Initial idea, maybe some people use it in the past, but this doesn't solve all the problems. No protection and cannot load the whole programs to the memory at once. Okay. Another another solution might be another solution might be this. Okay. Base and limit registers. Okay. Base and limit registers. So in this case, we are going to get some help from the hardware. Okay. Get some help from the hardware. Hardware is going to be this. Each program will have a base register and the limit register. Okay. This base register is this contains for program B. This is my base register. Program A, my base register is 0. So starting address. For the program A, the limit register is this one. Okay, 16380. Okay. Okay, so two more registers CPU will support it. Okay, CPU will support it, and this is what happens. Okay, map each process's address space onto a different part of the physical memory. Contents of the base register is added to all memory references. Whenever I do such a thing, jump 28, the hardware automatically adds 28 with this base register. Now I get whatever I want. I get 16 for 12. Okay, so this addition is dynamic. Remember the static relocation? It's not static relocation. It is dynamic and it is done by the hardware. It's done by the hardware. And hardware is something like this. Remember our CPU? This is our CPU. This is our memory. And these two are connected, right? These two are connected. But memory is not connected, but the CPU is not connected to the bus directly. It is connected through this MMU, Memory Management Unit. Memory Management Unit. Okay. So this Memory Management Unit has two registers in them. One is the base register. The other one is the limit register. Whenever CPU says that jump 38, okay, this memory management unit adds the content of this base register, okay, base register with this number, and the memory will get this added value automatically. Okay, and when the context switch happens between two processes, of course, I change the base register and limit register every time. Okay, so remember I have lots of registers. I have my stack pointer. Okay, I have my register 1, register 2. I have my program counter, status word, and etc. So I added two more registers. So that's it. That's as simple as this. Okay, so we solved problems with this one, especially the protection, because if the added value is larger than the limit register, then the hardware produces an interrupt, and the interrupt is handled by the operating system. So that would be a segmentation fault or the limit fault, memory fault. Okay, so there is protection too. I cannot, if the produce address is larger than this limit register for A, okay, then the hardware will not let this happen. So protection is solved. Okay, tell me the bad part of this solution. Tell me the bad part for the solution.
Till I am loading all my program info to memory.
Yeah, exactly. I still have to load the whole program. Okay, I still have to load the whole program into memory for A and B. Okay, that's the thing. Okay, so we need to solve that one somehow, and we are going to do some swapping, and we are going to see that. Okay, so before going further, let's look at this definitions, a few of them. So the memory abstraction is this: multi-programming and memory protection are not easy without abstraction. Okay, so abstracting away the details of memory. So as you see, we will have this kind of stuff, memory management unit, and they are part of the memory management. So we need okay, memory abstraction. Address space is the abstraction for the memory. Processes and threads are the abstraction mechanisms of CPUs, and they are supported by the operating systems. Now we are going to use this abstraction mechanism of address space, okay, to manage the memory and to abstract away its details. Okay, so each process has its own address space, independent of the other processes or the operating system. Okay, like this one, right? Like this one. This one thinks that it is using. This one thinks that it is using the address number 28. And in fact, operating system and hardware is changing all of these memory references with these numbers, right? So it is not using physically address number 28, but it thinks that it is using address number 28. Okay, so that's the address space. Okay, each process thinks that it has its own address space, and the address space starts from some number 0, and it goes to up to some large number. Okay, but those are virtual addresses. Those are not physical addresses. Those are logical addresses. And the operating system and the hardware is responsible from translating, making this translation all the time. Okay. It's like the processes again. Remember with the processes, each process thinks that it as a CPU and CPU belongs to it. But in fact, it is time sharing the CPU with other processes. In this case, each process thinks that it has its own address space starting from 0 to some number, and it doesn't know that physically it is not using the address number 0. It is using someplace else, and it is space sharing the memory. It is whole memory doesn't belong to it. Okay, memory is shared between the other processes. Okay, while we are doing this, we have to handle the protection and relocation. We are going to see this in a few minutes. Protection, the base and limit registers are kind of the answer for the relocation, and we are going to see in a few minutes. But before that, I think we need to go to, yeah, so go to the, did you bring your computer? Yes, I did. Okay. We need to go to, okay, I'm going to stop this. Our quiz will start at 9. So go to the our our page, our Teams page. Where is our Teams page? Yeah. And from the, I guess from the homeworks or something like that. Yeah. Do you see the quiz? Do you guys see the quiz? Do you see quiz?
I'm open. I cannot see.
Well, now you should see it now. Do you guys see it? Okay, everybody turn on your cameras. I need to see you.
I can see, sir.
Turn on the cameras.
I can't see.
Turn on the cameras.
I can see there.
Okay, do you see the quiz now?
No.
I don't see right now, sir.
Just wait a minute.
I can see.
Okay, you should see it now. Do you see it?
Yes.
Okay. You may start now. Dokan, I don't see your face.
Gözükmüyor mu hocam? Bir saniye. Telefondan gireyim.
Ersel Celal, your camera is not on.
Şu an gözüküyor mu? Ben kendimi görebiliyorum ama.
Why are you talking in Turkish?
I can see myself in my
No,
chats.
I don't see you. Mohammed Sefa, I can't see your image.
Sir, I opened the camera, but I think there's a problem with permission. I'm trying to fix it. Hi. Sir, can you see right now?
You should submit your quiz before the end time, which is 9:20. After the end time, we can't accept your results, okay? Your quizzes.
Sorry, can you repeat?
You should submit your quizzes before the end time. When the time ends, I can't accept any quizzes. So submit it by 9:18 or something. Okay, time is up. Submit your quizzes. Everybody, submit your quizzes right now. From now on, anybody submitting, they will be considered late. Okay, if you submitted it, you can turn off your camera if you like. Anybody couldn't submit yet? Did everybody submit the quiz? I guess so. Okay, good. So I have how many? I have 161 submissions, which is good enough. By the way, many people did not turn on their cameras. That will be reflected in your grades.
Sir, I opened up my camera before the quiz start, and it was working. After I checked it, it wasn't working.
Same as me.
Okay, 2 people submitted it late for some reason. Okay. Okay, let's go back to the lecture and we are going to see. Okay, so are there spaces? If you well, let's go over the the quiz actually. Let me try to get to the quiz. Okay, here. Yeah, like this. So, like we did in the lecture, we have converted the 5 philosophers dining philosophers problem into a linear one instead of the circular one, and we said that describe a give me a set of steps that will cause deadlock. And like the last time, actually, since the resources are taken in order from 1, 2, 2, 3, 3, 4, this is a very nice deadlock prevention algorithm. There is, I mean, you can't produce any deadlock based on the resource usage. That's what we said yesterday, right? So I can't produce anything is the correct answer. For the second one, okay, for the second one, uh, monitors are directly supported by Java. When you say a procedure a method is a synchronized method, it's part of the monitor. Whenever it is called, it is automatically locked. Okay, so that has the advantage of the monitors, right? In C++, thing, okay?
Düzeldi sanırım hocam.
Couldn't hear you.
Okay, for some reason I got interrupted. I don't know why. So for the second question, since Java directly supports monitors, I don't have to remember about anything mutually exclusive stuff. But in C++, I have to use both wait and notify. That's one thing. Also, I need to lock the critical region too. In Java, I don't do this, so that's the answer. Okay, so good. Okay, let's go back. Any questions about the quiz?
What's the percentage? Like, do you know? Did you decide?
No. Well, I mean, I think I'm going to read the results and I'm going to look at the cheating ratio. And if I realize that people have cheated a lot, then this will not be worth much. If it is not, then I will filter out the cheaters. Then rest of them will get their fair grades, etc.
Sir,
Okay.
there was like 20 people who couldn't send in the first quiz, but the İlhan Hoca didn't do anything until yet. So what we will do?
So are you asking this right now?
Sir, it was like 2-3 weeks ago, but
No,
İlhan
are you
said
asking this right
I
now?
will talk with you, but I guess he didn't.
Okay, send him an email and copy. Keep me in the copy part, okay? I think İlhan already addressed that too. That's what I thought. Okay, any questions about the quiz? I mean, the material part of the quiz? Or the content of it?
Teacher,
Okay.
we wasn't ready, I think, for this quiz. Yesterday night we have homework, and for at least for me, for my case.
Okay, so one night of study was not enough, you are saying?
Yes, and I don't know if, those questions, which lecture, but I couldn't attend the last lecture yesterday, and I miss, I think, some parts. I was knowing the producer consumer problems and process threads, some kind of stuff, but I missed the questions.
Okay, but you are supposed to attend the course. I mean, that's why I decided to make it, because nobody was listening, nobody was answering my questions. And many people, maybe like you, didn't attend the class. Maybe they just look like attending it. That's why I did the quiz. And it was obvious that I was going to ask questions about yesterday's lecture. Nobody was listening. Okay, let's move on then. So address space is something that we define. This way, every process has its own address space. And in fact, that address space is not physical, it is all logical. The processes see it that way, just like they see the CPU. They don't know that they are sharing the CPU. Address space is something that they think that they have. But in fact, the operating system, with the help of hardware, of course, it is managed. And one example of this is base and limit registers, of course. To manage the memory, you need help from the hardware, okay? Hardware has to add all these base register values to your memory references. Whenever you do that, okay? Operating system cannot add those values for you, because operating system is a software, right? It's a piece of software. It cannot, I mean, you are not doing any system calls to add two values. So all the operating system does it. Whenever a new process starts, it says the a base register and the limit register. That's it. The rest of them is handled by the memory management unit. By the way, setting these registers requires privileged instructions because no ordinary process should be able to change their values. So memory management programming, okay, memory management unit programming, memory manager programming is something privileged than we are going to see. It is more complicated than that, though. It has many more registers in it. So disadvantage of this base and limit registers is every memory reference is an addition. Addition is expensive. Why expensive? Because with the addition, you have to do this. If I had to add these two binary numbers, okay, I need to do this, add these two, 0, and look at the carry. There is no carry, add these two, 1. There is no carry, add these two. It is 0, but there is a carry. Add these two plus the carry, it is 0, but there is a carry. Again, 1, and then I guess 1, right? So it has to go this way. So it is sequential. If it is sequential, then it's going to take time. It is expensive. Okay? That's one thing. So it's going to be expensive to make this addition all the time. We have to find something different than addition. Okay? And again, large programs do not fit in the memory. Okay? So the solution would be maybe swapping. Let's look at the idea of this swapping. Okay? Swapping is this. Let's say I like to have an operating system and many programs in my memory. Using base and limit registers, I loaded my program A and space register here, limit register here. A runs nicely. Then I loaded this program B. Okay, they are both running nicely. They have their own base and limit registers. Every time I do a process switch, I do this. And then I loaded this program C. Okay, I loaded this program C. But then I need to load a new program D. Okay, a new program D. I don't have enough space. So what am I going to do? I am removing this A. See, I remove this A. I wrote it back to maybe some part of it back to disk. Now I have enough space and I am loading this program B. Okay, so what I'm doing is I keep loading programs. Well, I have to load my programs anyway, but when the memory is not enough, now I have to unload this program A and I need to load the program D. Okay, and I have to switch to program A back to A because A did not finish yet. It is running. So I don't have enough space. What am I going to do? Maybe if I had these two, okay, in a contiguous configuration, maybe A would have been enough. Okay, that space would have been enough, but it is not in a contiguous configuration. Then I have to swap out this B and load A back again. Okay, load A back again. One solution would have been maybe this. Maybe, okay, this is my operating system. Put D here and move B here, C there. Now I have enough space for A. So this is called compaction. When you compact your memory, you might have enough space for A, okay? For A like that. Okay, but compaction is expensive. You have to move the processes around a lot. And the swapping the whole programs back and forth between the main memory and your disk, okay, is going to be expensive. Okay. Physical memory is not large enough to hold all processes. That's what we know. Okay. And swapping might be a solution. Write the entire program out to disk when it is blocked. Okay. And read it back again whenever it is ready to run again. And from time to time, I have to compact the memory, move the processes around so that I have enough contiguous space for some of the processes. But the main problem with the swapping is, again, it is the disk access. Disk access is millions of times slower than memory access. If every time you need to do this, okay, if every time you need to do this, then you will have lots of inefficiency issues. Okay, I mean you think that you think that you are running 3-4 programs at the same time, but it becomes so slow that your operating system and total computer system is not usable. Okay, so swapping as it is like this is not usable much. Okay, is not usable much. So we have to find another solution, maybe this virtual memory and partial programs. This is interesting, partial programs, and maybe we can use this. What do we mean by partial programs? This was tried before. The partial programs are this. As a programmer, as a software developer of program A, I say that my program consists of 1, 2, 3, 4 parts. Okay, these are overlays. Overlay number 1, overlay number 2, number 3, and number 4. Okay, so whenever the operating system needs to swap out my program, it doesn't have to swap out the whole program, but some part of it. It is okay. Or the program itself overlays it. The program says that I am going to keep overlay number 1 and 2 in my memory, and rest of them can stay on the disk. Okay, so it's a partial program. This kind of helps our problem of not all programs fitting in the memory. That's true, but it's not a complete solution. You need lots of help from the software developer, and the software developer needs to know about the details of the memory, right? What fits in the memory, what doesn't fit. When should I swap out? When should I swap in, etc. So that's not a very good solution either, but it's a solution. Okay, it's a solution. Good. So with the virtual memory, we are going to provide another solution, and that will be a nice solution. Okay. Let me skip this part. Okay. So we say that when the memory is assigned dynamically, operating system must manage it. We know that. Okay. Then operating system should know what part of the memory is free and what part of the memory is not free. Okay. And it should keep some kind of a data structure about it. And that data structure will be in the form of, how come I have these? How come I have these? Okay, it could be like a bitmap. Let's say this is my whole program. This is my whole memory. Okay, and I use a bit for each 16 kilobytes of memory. 16K, 16K, and 16K. I keep a bitmap. Okay, I keep a bitmap for each 16Ks. One bit represents a 16K. And if I keep this bitmap, it will tell me which parts of the memory is free and which parts are not free. And I can do my compaction algorithm on this bitmap. So I'm not going to look at these bitmaps or the linked list structure different from last year because we don't use them anymore much. Instead, we have our other better ways of doing stuff. Okay, let me go to, so I'm going to skip this memory management algorithms, first fit, next fit, best fit, etc. I will skip those. Okay, I talked about the overlays. Let's come to this virtual memory. Virtual memory is, okay, is something that we use all the time. This is an ultimate solution. It eliminates all the problems of allocation inefficiency, compaction, relocation, memory protection, and more. So it solves many problems at the same time. Okay, it solves many problems at the same time, and each program would think that they have their own address space. They don't have to think about swapping. They don't have to think about protection issues. Okay, and it works this way. Remember our memory management unit inside the CPU, right? Every time I make a memory reference from the CPU instruction, this memory management unit translates the memory address from my virtual address space, okay, from virtual memory to physical memory, okay? And this is how it is done. Let's assume that, okay, I have only 32 kilobytes of physical memory. That's what I have, okay? That's what I have. 32 kilobytes of memory. Okay, physical memory I have. But my address space, my virtual address space, runs from address number 0 to address number 64K. So my process thinks that it has 64 kilobytes of memory. So how is that going to work? Okay, how is that going to work? This is what we do. We divide our virtual page into, okay, our virtual address space into virtual pages, and each of them is 4 kilobytes large. It's 4K and 4K, 4K, etc. Okay, this is our virtual page. Whenever I need to access something, okay, let's say my program is trying to jump address number 5252. Okay, I know that it is inside this one, okay, inside this virtual page, but in reality there is a table that says that this virtual page is in the memory here. Okay, in physical memory, by coincidence, let's make this a little bit different so that, okay, let's say jump 9050. Okay, so 9050 is inside this virtual page, but my virtual page table takes this address, okay, and places it into this physical memory page, physical page frame. Okay, in reality, my address in this box, in this 4 kilobytes of space, but in virtual memory, I do it this way. So there is a translation going on all the time. There is a translation going on all the time. Every time I make a memory reference, this memory management unit, okay, gets that address, that virtual address, and translates it to this physical memory address. you might say that it is like base and limit registers, kind of similar, but no, it is not a simple addition. It is a little bit different. It is cheaper, but it is more involved, and we are going to see how it works. Okay, let's look at this example now then. Example is here. It is the same example. Let's say I am trying to access, okay, how many bits are there? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So 16 bits. 2 to the 16 is what? What is 2 to the 16?
32.
Hold on a minute. Efendim? Aleykümselam. Hocam, Şükrü'yüm hocam, bir dersteyim, acil mi? Ben ararım ders bitince hocam. Tamam, görüşürüz. Okay, so it is just 16 bits. Okay, and is it? Okay, so it is 16 bits. Okay, it is 2 to the 16 is 32 kilobytes. Is that correct?
64 kilobytes.
Yeah, it is 64. Yes, 64. 64, then 28. So 2 to the 20 is 1K, right? It is 19 is 12. 18 is 120, right? 17 is, this is 500, 120. 2 to the 16 is what? Really? We don't know. Is it 32 or 2 to the power? And I don't know how to type power. Like this. 16. Yeah, it is 65. So it is 64 kilobytes of address. I can, let's say this is an address, my virtual address, okay, my virtual address. I can address 64 kilobytes of memory from 0 to 64 kilobytes, like this one, 0 to 64 kilobytes, like this one. And my virtual address is coming in this way. So this is what I do. This is what I do. I divide this into two parts. 4-bit part, 4 bits. Okay, this is a 4-bit part and 12-bit part. Okay. Maybe this 12-bit part is like this. And I keep this 12-bit part as it is without any modification. But this 4-bit part is going to tell me my page number. Okay, this one says that your page number is, okay, virtual page number is 0010. That is page number 2, right? So this is my page table. Inside this page table, okay, given my virtual page number, I find the corresponding physical page address. Okay, 0010, it is the number 2. It one says that your physical page number is going to be 110, that is 6. Okay, that is 6. It is exactly like this, okay? This is 0, 1, 2, okay? Inside this number 2, this page lookup table number 2, the number here is 6. So 6 means that 0, 1, 2, 3, 4, 5, 6. So it is pointing to this one. Okay, so this is what the memory management unit holds. This is what page table holds. Say that whenever I get this page number, virtual page number 2, I am going to replace it with real page number, physical page number 101. So this part, again, is same as this part. So I just directly put it in there. I didn't make any change. But this part, I will get it from here, translate it to 101, and put it in here. So 101 will go in there. Okay. So this is how many bits are there? So there are a total of 15 bits. Okay, there are a total of 15 bits in here. 15 bits is 2 to the 15. That means at most 32 kilobytes. Right? So this is what I do, but this is what I did inside my memory management unit, like here. Every time CPU makes a memory reference, I look up my virtual page number from the page table, and I replace that virtual page number with the physical page frame, and I output that 15-bit address to the memory. CPU instruction thinks that it is accessing a 64-bit memory, but in fact in the memory, I am accessing a 32 kilobytes of memory. Okay, so this is done all the time. This is all the time. Whenever memory access happens, you might say that isn't this expensive? No, because this is like the cache memory. This is like the cache memory. It's an associative memory. Associative memory. Okay, it is an associative memory, and this associative memory is very quick. It can do this lookup in a very quick amount of time. It's not sequential like the addition. Whenever you give it to this memory type, it produces this number. Okay, it produces this number. So this is very quick, and inside the memory management unit, I keep this table. Okay, this table will translate your virtual page numbers into physical page frames. By the way, some of them it looks like, see, these are 000. Okay, 000. That means that that page is not available. It is not loaded in my physical memory. If I go there, right? So this one, X means that it is not loaded, right? It is expected, right? I mean, my virtual memory is 64 kilobytes, my physical memory is 32 kilobytes, and some of them will not fit into my memory. So what happens if I try to access something in this box? Okay, memory management unit is going to tell me that that address is not available. Okay, memory management unit is going to tell me that that address is not available. If it is not available, then I cannot load it. So what's going to happen? Maybe I need to get rid of this page, write it back to the desk. Okay, and now maybe I am going to say that I don't need this page anymore. Get rid of it, and now I am going to point this here. Okay, and I am going to load it from the desk. I'm going to load it from the desk. Now I can use this part. as my part of the virtual memory. Okay, so this is how virtual memory works. Did we prevent swapping? No, of course not. Swapping will not happen, but I don't have to swap the whole program, right? I swap parts of it. I swap parts of it. And the other nice thing is, as you see, my program doesn't have to be kept contiguously on the physical memory. As you see, first this page is here. My beginning of the program is here. At the beginning it is, let's number them, okay? At the beginning, this is number 0, then this is number 1, then this is number 2, and this is number 3. So my pages are all over the physical memory. They are not contiguously sorted anywhere. So order doesn't matter. I can change the positions of these pages from anywhere to anywhere that I like. And I don't have to keep all the pages in the physical memory. Most of them can stay on the desk if they are not used. So these are all the nice features of virtual memory and the paging. What did we say about it? It eliminates, for example, I don't have to do compaction. Can anybody tell me why? Why don't I need compaction in this virtual memory with paging? I don't need compaction. Remember with the compaction, what did we do? We did this. Where is it? Oh, okay. With the compaction, even though I have enough memory for I couldn't fit in, I need to move things around, right? Now I don't have to do compaction. Can anybody tell me why I don't need compaction?
Because my process is already divided into parts.
Into parts, and those parts they don't have to be in order, right? I mean, I can change their order, and as long as they are in the form of 4K chunks, they can stay anywhere in the memory. Okay, I don't have to move them around, and if I move them around, that's okay. If I move them around, all I have to do is I just change this page table inside the main memory management unit. I don't need compaction. Okay. What else? I don't have to relocate anything. And memory protection is there too. Okay, memory protection is there too, because my table here, see this one. This one says that this is my physical address. This is my present bed. Do I have that page in the memory or not? Okay. And then I have more fields like this. How about my read permissions, write permissions, execute permissions? Okay. And how about my process ID? I can put that kind of information inside this page table. So whenever somebody accesses it, is it for the reading, writing, execution, and I know which process owns this page too. Okay, I know which process owns this page too, and that makes it automatically robust against protection problems. Okay, so it is very advantageous. That's why we like it. And we don't have to talk about, but I mean, I don't have to keep the nicest thing is I don't have to keep my whole program in the memory, okay? I only load the necessary parts. Only load the necessary part. The rest of them can stay on the desk. That's how I can fit hundreds of programs to my 16 gigabytes of memory even though each one thinks that they have their own 64 gigabyte of memory or 48 gigabytes of memory. Okay? They can't have that kind of memory, but they think that they have it because of the paging. Okay? Any questions about paging? From now on, we will keep talking about paging. Paging is something that we use all the time. Modern operating systems and hardware, in combination, they utilize this idea of paging. It was invented in 1960s, and we still keep using it. And in fact, if you go to your task manager, somewhere on your memory, okay, there is this page pools. Okay, there is this page pools. These are when they say bellek havuzu, it's a page pool. Okay, so on my computer I have this many page pools are available. As I said before, even though I am running this many processes, hundreds of processes, okay, hundreds of processes, they keep only a very small amount of memory, physical memory. Rest of them will stay on the disk. Disk is large. Okay. Whenever my program becomes active, it starts using more memory because it gets more pages from the free page pool. Okay. Free page pool. Okay. And this one shows, I mean, with the hundreds of programs loaded, I shouldn't have any memory available, right? But that's not the case. Of course, I keep some pages available. It's all free because as an operating system, I like to keep some pages free. That's why that way it would be very easy, very fast to load new programs or load parts of the programs very efficiently to the memory.
Hocam,
Yes.
why do we need the bigger page table than the physical physical memory?
Well, this program thinks that it has 64 kilobytes of memory, right? It needs 64 kilobytes of memory to run. Otherwise, this program cannot run. It is written that way. You don't
But
need it.
our system doesn't support the 64 kilobyte. So how it
That's
works?
that's the nice thing. Okay. At a given time, I can only keep 32 kilobytes of memory. But because of the principle of locality, do you guys remember this principle of locality? Do you guys remember principle of locality from your hardware courses? It says that let's say I have a program, very large program, okay, address number 0 to 64. If I am executing instructions around here, the next instruction I am going to execute is going to be around this region, 99% of the time. Okay. If you access part of the memory, next time you access part of the memory, it will be around this part. Okay. That's the principle of locality. That's the main working principle of the cache. Okay. Working principle of the cache. So principle of locality says that even though you need 64 kilobytes of memory, all you are using it maybe 2 or 3 pages of your memory at the same time, similar time. From time to time, maybe you are going to use some other pages. Okay, in that case, I am going to load those pages back to the physical memory. Okay, so it is okay to keep only part of your program in the physical memory. Rest of them can stay on the disk. And without swapping much, I can continue. Okay.
Thank you hocam.
Did I answer your question?
Yes hocam, thank you.
So that solves lots of problems. I mean, I can load many programs to my memory. Okay, each one has its own virtual address space. Compaction is not needed. I don't do much swapping at all. All I need is just some hardware help. All I need is some hardware help. Do this translation. And this translation needs this cache memory, associative memory. Okay. I get a number in here. I look it up very fast. I find its corresponding value and I paste it in there and I get this. I put in 16 bits, I get 15 bits back. All I do is I replace the top 4 bits with this 3 bits. Rest of them stays the same. So this one address is inside the page, physical page. And this one is a virtual page number. This one is the physical page frame number. Good. So implementing the virtual memory is okay. These are the definitions. We already did that, right? So this is my physical memory. Each 4 kilobyte chunk of it is called a page frame. This is my virtual memory. Each 4 kilobyte is called a virtual page. Okay. We already said that. Pages
Can I ask a
virtual
question?
page, and then this one. Yeah, sure, yeah.
Can a process consist of just 1 or 2 kilobytes of data?
Sure, why not?
Then can the two of such processes be placed in the same page?
Oh, no. This is the least amount of memory that you can use. 4K is your basic unit. Okay. If you are a process that needs only 1 kilobyte of memory, then you have to use your whole page, 4 kilobytes. Less than 4 kilobytes, okay, you are going to waste some part of it. Okay, so let's say you are using only this much, rest of them will go unused. Okay. And this one, I mean, the way you ask your question is, if I have a process that uses 1 or 2 kilobytes, right? This is this happens all the time. You don't have to do it that way. Let's say I have 10 kilobytes of memory. Okay. With the 10 kilobytes, how many page frames do I need? I need 1, 2, and half of the 3, right? So the last one, half of the last one is going to be wasted. So 4 kilobytes here, 4 kilobytes here, and 2 kilobytes here, right? That's called internal fragmentation. Internal fragmentation. And it is not avoidable. Internal fragmentation will happen. All the processes, the last frame that you are using, on the average, half of them will be wasted. So that you don't like very large page frames, okay? If you have page frames of, let's say, 16 kilobytes. They are very large. Okay, they are very large. So for some processes, 8 kilobytes of them will be wasted. We don't like it much. That's why we keep our page frames small, okay? Small, like 4 kilobytes. Okay, small, like 4 kilobytes. So what is the problem with 1 kilobyte page table, okay, page frame size, or 128 byte page frame? So what is the problem? I told you the problem with the large page table, page frame size. What is the problem with the very small ones? If I keep my page sizes very, very small, like half a kilobyte or 128 bytes, what's the problem with that?
External fragmentation.
Well, the nice thing is with the paging, there is no external fragmentation because everywhere is used, right? This is external fragmentation. This one here is external fragmentation because these places sometimes are not usable. I have to move things around, but I don't have external fragmentation with paging. I completely eliminated it. Why? Because every place I can use it for anything. I have internal fragmentation, and I prevented internal fragmentation by keeping my frame pages, page frames, very, very small. They are half a kilobyte, okay? But there is a problem with this. If my page frames are very small, what?
It will require longer addresses to access them.
The addresses are the same, no? Well, addresses would have been the same. It is
The
still
size of the virtual address table
yeah,
will increase.
exactly. Yeah. See, if I have here, if I have 4 kilobytes, pages, then this 14-bit offset is enough for me, right? 14-bit, because 14-bit means 2 to the 14 is 4 kilobytes, right? 4 kilobytes. But if I have, let's say, half a kilobyte page tables, pages, then it's going to be 2 to the 9. It is 512 bytes. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be my offset, and this one will be my frame number. So this is 1, 2, 3, 4, 5, 6, 8. 2 to the 8. 2 to the 8 means that I have to keep 256 elements inside this page table. Okay, 256 elements. This is a very expensive place because this is part of the MMU. MMU is part of the CPU package, and each one is a register, right? So that's too expensive. So you don't want to keep your page table very large. You don't want to keep it very small. You don't want to keep it very large. You have to keep the balance. That's why most of the time, 4 kilobyte page sizes are good enough. And in fact, let's go to our chat GPT and ask what kind of pages. Okay, maybe. Yeah, okay. What is the page size, virtual page size for Windows 11? So it is not just a single value, it is selectable. typically dependent on the hardware architecture, etc. But Windows 11 tend to use virtual page size of 4 kilobytes or 8 kilobytes. Okay. Okay. So it is sometimes it is selectable, sometimes it is not. How about ask the same question for Linux? Is typically 4 kilobytes. See, but it can support larger page sizes such as 2 megabytes or 1 gigabyte. Okay. So in that case, you don't care about internal fragmentation, maybe. Okay. In that case, you are going maybe for some server applications where you don't have many clients. In that case, I can use gigabytes, but usually it is 4 kilobytes. I hope those values are true, but they are logical. I mean, we don't use ChatGPT to get definite answers. We get kind of approximate answers, so those numbers might be not correct, but they sound fine. Okay, good. And this is how you do the translation. Actually, it is very easy. You have a virtual address. Remember my 16-bit address? I have my virtual 16-bit address. Okay. And I get the 16-bit address. I divide it into two, 4-bit part and 12-bit part. This is 12 because my page size is, virtual page size is 2 kilobytes, so it is 2 to the 12. And this is going to be used as a lookup index. So I divide this address into two. I divide the virtual address into two, V part and O part. O is the offset, V is the virtual page number. Then MMU takes this part, the virtual part. Offset part will not be changed at all. MMU will map V into P. So V will be changed to, okay, V will be changed to, okay, this O will stay the same. It will be changed to P. So it is, instead of 4 bits, I will now have 3 bits. So V will be translated, V will be translated to P. So this is what I do. It's basically an array, right? There is an array. I put my index of V into this array, and it gives me a 3-bit number back. And I put them together, and we get our physical address back. Okay, and this is faster than base and limit registers. This is faster than base and limit registers. Okay, no additions are involved. You just combine these two. And this lookup procedure is done by the associative memory, and that's why it is faster. Okay. Good. Any questions? Just try to see I think there was a way of how to show details of Windows page table. Okay, memory. This talks about this is a This is directly from Microsoft. Okay. Didn't work much. Where is the page table? Well, you can't get the whole page table, but there is some monitoring information about the page table. Couldn't find it. As always, I could not find it. But I think you can get more information about each process and their page tables and etc. Especially the page faults. Word. Okay, these are the memory being used, active memory. Can I do this? No, I can't. I couldn't get it. I think I can add more stuff. No, I couldn't find it. Sorry. Okay, I'm out of my time for today. Are there any questions? There are no questions, then we will continue next week. Okay.
Okay.
Bye now.
Thank you. Bye.
Have a good day.
Nice day.
You too. Thank you.